In the cold dark of space, where light from the sun fades into blackness, a series of silent beacons drift endlessly. Each one carries the same fragile signature, the echo of human curiosity. They are machines built of metal and wire, but also of hope. Launched decades apart, they trace invisible lines between the planets, chronicling our long obsession with the worlds that orbit beside us. Jupiter, Saturn, Mars, three very different planets, yet bound together by a single thread, our relentless desire to understand what lies beyond Earth. From the gas-choked storms of Jupiter to the frozen deserts of Mars, every mission sent their way became both a technical gamble and a philosophical mirror. What we found out there changed not only our science, but our sense of what it means to exist in the universe. The story begins in the early age of space exploration, a time when telescopes could glimpse, but not touch, the mysteries of the outer planets. The ancient astronomers had seen them as gods: Jupiter, the ruler of the heavens; Saturn, the keeper of time; Mars, the bringer of war. Centuries later, as the space age dawned, we began reaching for these distant deities with fragile mechanical hands. The first probes were crude, built in the shadow of the Cold War, when exploration was as much about national pride as scientific pursuit. Pioneer, Voyager, Galileo, Cassini, Juno, each name now etched into history, carried our instruments, our questions, and our fears into the void. With every new image, humanity saw its reflection sharpen. Planets that once appeared as blurred dots became complex worlds of storms, oceans, and hidden energy. And yet, the more we learned, the less we understood. Why does Jupiter's magnetic field behave like a living thing, shifting and pulsing in ways we can't predict? What keeps Saturn's rings suspended in their perfect geometry, despite the laws of chaos? Could Mars, dry, red, silent, still hide the chemistry of life in its dust? Each discovery only opened new mysteries. Probes malfunctioned, antennas failed to deploy, solar panels froze, data arrived incomplete or not at all. Still, mission after mission continued because the silence of space demands answers. This is not merely the story of technology. It is the story of a species standing on the edge of the cosmic ocean, sending fragile messengers into the dark. It is a story of risk, patience, and revelation. How humanity learned to listen to the whispers of the planets. Over the next chapters, we will follow this journey. From the first blurred images of Jupiter to the final plunge of Cassini into Saturn's atmosphere. From the dust storms of Mars to the icy oceans of Europa and Enceladus. Each mission revealed not only the nature of the worlds around us, but something deeper, the nature of ourselves. Because in the end, every spacecraft ever sent across the solar system carries one message engraved in silence. We were here, and we wanted to know. Part 1. The awakening of the giants. For centuries, Jupiter and Saturn had been symbols of cosmic order, two glowing beacons that ruled the night sky. They drifted beyond the reach of ancient astronomers, their motions predictable yet their nature unknown. Through Galileo's telescope in 1610, Jupiter's moons revealed themselves as a miniature solar system, a scandalous idea at a time when Earth was believed to sit at the center of creation. But what Galileo saw was only the beginning of a mystery that would take 4 centuries to unravel. By the middle of the 20th century, humanity had finally built the means to cross the gulf of space. Rockets that once carried weapons were redesigned to carry instruments. When the United States founded NASA in 1958, the dream of reaching other planets shifted from fantasy to engineering. Still, no one truly knew what awaited beyond Mars. The asteroid belt, a vast region filled with tumbling rock and debris, was feared to be an impassable graveyard for spacecraft. That fear didn't last long. In 1972, NASA launched Pioneer 10, a small, unassuming probe built in California's Jet Propulsion Laboratory. It was no larger than a modern refrigerator, its panels coated in thin aluminum to withstand micrometeorite strikes. Its mission: to become the first machine to reach Jupiter and survive the crossing of the asteroid belt. As it coasted away from Earth, Pioneer 10 carried a golden plaque, a simple map, etched with the position of our sun, the outline of a man and woman, and the binary pulse of hydrogen. It was humanity's first interstellar calling card. When scientists fastened it to the probe's frame, they understood the gesture was more symbolic than practical. No one expected an alien civilization to find it, but the plaque meant something else. It was proof that, even at the dawn of deep space exploration, we wanted to be known. The journey to Jupiter took more than a year. By December 1973, the probe began transmitting images. Ghostly, pixelated frames showing the planet's cloud tops, swirled with color and motion. For the first time, humans were seeing Jupiter not as a disk through a telescope, but as a world. Its great red spot, a swirling oval of storm larger than the entire Earth, churned with energy that defied explanation. The readings were staggering. Radiation levels around Jupiter were 10,000 times stronger than Earth's Van Allen belts. The probe was nearly blinded by static interference, its circuits flooding with electric noise. But Pioneer 10 endured. As it passed behind the planet, its trajectory curved outward, accelerated by Jupiter's immense gravity. The effect was dramatic. The probe's speed more than doubled, turning the gas giant into a cosmic slingshot. This gravitational assist would become one of the most valuable tools in interplanetary navigation, allowing future missions to reach multiple planets on a single trip. Encouraged by the success, NASA sent Pioneer 11 soon after. Its goal was Saturn, a world no human had ever seen in detail. Yet before it reached the ringed planet, it, too, flew past Jupiter, confirming and expanding the data from its twin. When Pioneer 11 continued toward the outer solar system, engineers at JPL realized something profound. They could do more than just visit one world at a time. In 1964, a young engineer named Gary Flandreau noticed a rare alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, an event that occurred only once every 176 years. With careful timing, a single spacecraft could use gravity to leapfrog from one planet to the next, like stepping stones across the cosmic river. NASA called the idea the Grand Tour. By the mid-1970s, plans for the Grand Tour had evolved into something bolder. 2 identical probes would be built, tougher, smarter, and more autonomous than anything that came before. Their names would become legends, Voyager 1 and Voyager 2. In August 1977, the first of them launched from Cape Canaveral, its silver body glinting in the Florida sunlight. 16 days later, its twin followed. Each carried a golden record containing the sounds of Earth, a message to eternity. Greetings in 55 languages, the hum of a heartbeat, the crash of waves, the laughter of children. The Voyagers were not just instruments. They were time capsules of human existence. But just before their departure, a problem emerged. Data from Pioneer 10 revealed Jupiter's radiation could destroy the Voyager's delicate circuits. Engineers scrambled. With no time to rebuild, they resorted to something astonishingly simple: supermarket aluminum foil. They wrapped the cables in layers of kitchen-grade foil, shielding the probes from electrical surges as they raced past the gas giant. It worked. In 1979, Voyager 1 reached Jupiter. The images it sent back transformed astronomy. The planet's clouds were alive with movement, ribbons of ammonia and hydrogen stretching for thousands of kilometers. Lightning storms larger than continents flashed in the darkness. And orbiting nearby were 4 worlds that shattered every assumption scientists held about moons. Io, bright yellow and volcanic, was scarred by eruptions that shot plumes hundreds of kilometers high, the first evidence of active geology beyond Earth. Europa gleamed white, its surface as smooth as glass. Beneath its ice crust, instruments detected an ocean vast, dark, and liquid. Ganymede and Callisto revealed ancient scars and magnetic fields of their own. Humanity's perception of the solar system changed in an instant. Moons were no longer dead rocks. They were worlds, each with its own character, its own secrets. For the scientists at NASA's Jet Propulsion Laboratory, the discovery was overwhelming. During the flyby, data streamed in faster than any team could process. For days, Researchers slept in hallways, surrounded by reels of film and computer printouts. They were witnessing the birth of a new science, planetary exploration on a scale that once belonged to imagination. When the Voyagers left Jupiter's gravitational well, they carried momentum, not only in velocity but in vision. Ahead of them waited Saturn, its rings shimmering in the dark. The age of the giants had begun. Part 2. The rings of time in the vast darkness beyond Jupiter. The sun shrinks to a pale ember. Temperatures drop, radiation fades, and time itself seems to slow. Here drifts a world of quiet grandeur, Saturn, the Lord of the Rings. For centuries, its beauty has defied comprehension. Through Galileo's primitive telescope, it appeared as a planet with ears, its shape distorted by faint halos of light. Later astronomers realized those halos were rings, vast, thin bands of ice and dust encircling the planet like an ancient crown. But no one could explain how such a structure could exist, let alone endure. When Pioneer 11 approached Saturn in 1979, its mission was as much reconnaissance as discovery. Engineers at NASA's Jet Propulsion Laboratory knew that the rings could destroy a spacecraft in seconds if even a pebble-sized particle struck its hull. The probe was deliberately steered toward what they called a safe gap between the outer rings, ready to sacrifice itself if necessary to test the environment for future missions. As it passed the planet's southern hemisphere, Pioneer 11 survived. The probe returned ghostly, grainy images of Saturn's bands and revealed a new one, the F-ring, a narrow ribbon held in place by two small moons that shepherded its particles. It also detected unexpected heat from Saturn's interior and a powerful magnetic field, similar in strength to Jupiter's but strangely symmetrical. Then Voyager 1 arrived. By late 1980, the probe was closing in on Saturn, its cameras trained on the pale gold planet and its sprawling ring system. What it saw astonished scientists. The rings were not solid at all, but composed of billions of icy fragments, each orbiting independently. Within those rings were divisions, waves, and spirals shaped by the gravitational pull of nearby moons. Saturn was not a static world. It was an orchestra of motion, a dance of frozen debris locked in gravitational harmony. And then there were the moons. Voyager 1's cameras focused on Titan, the second largest moon in the solar system, larger even than Mercury. Its dense, orange haze obscured everything below. Instruments revealed an atmosphere thicker than Earth's, rich in nitrogen and methane. Beneath that veil, could there be seas, clouds, life? The data hinted at chemistry both familiar and alien. But the cameras could not see through the smog. Titan kept its secrets. After Titan, Voyager 1's path curved upward, away from the plane of the solar system. This planetary tour was over. Yet before it left, it turned its cameras back toward Saturn one final time. The resulting images, the rings viewed edge-on, glinting like blades of light, were among the most haunting photographs in the history of exploration. Almost a year later, Voyager 2 reached Saturn on a slightly different trajectory. Its cameras were functioning perfectly, and its mission plan was far more ambitious. It swept past the rings, revealing intricate structures that defied previous theories, braids, spokes, and ripples moving as if the planet's magnetism were stirring them. The F-ring flickered like a living thing, and gaps appeared where none should be. Saturn's moons revealed an entire miniature system, each one unique. Mimas, with its colossal crater, looked like the Death Star from science fiction. Tethys and Dione bore scars of ancient fractures. Rhea seemed coated in frozen frost. But one moon drew particular fascination. Enceladus, a small, dazzling sphere of ice. At the time, the images showed nothing unusual, just smooth plains and subtle ridges. Yet decades later, that little moon would change everything we thought we knew about life in the outer solar system. Having completed its survey, Voyager 2 performed another gravitational slingshot, gaining the speed it needed to continue toward Uranus and Neptune, the distant ice giants. For the first time, humans had eyes on all the major planets of the outer solar system. But Saturn still called to us. The serene beauty masked deep questions. How did the rings form? Why were they so bright, so pure, when cosmic dust should have darkened them over time? Were they ancient or transient, destined to vanish? And what, exactly, churned beneath Saturn's clouds, where hydrogen and helium swirl under pressure so great that rain might fall as liquid metal? For more than a decade, no spacecraft ventured that far again. The Voyagers continued outward, their signals growing fainter with each passing year. Back on Earth, the data they had collected kept scientists busy for decades. Yet even as we parsed the information, a new generation of researchers was imagining something far more ambitious. Not just a fleeting flyby, but a long-term mission to orbit Saturn itself. That dream would take shape as Cassini. In the late 1980s, engineers from NASA, the European Space Agency, and the Italian Space Agency began designing a spacecraft unlike any before it, heavy, complex, and built to survive years in the frigid outer solar system. It would take 7 years to reach Saturn, and once there, it would not simply pass by. It would stay. When Cassini launched in October 1997 atop a Titan IV rocket, it carried with it a small passenger Huygens, a European-built lander destined for Titan. Together, they represented one of the most ambitious collaborations in the history of planetary science. The journey was long. Cassini slingshot past Venus twice, then Earth, then Jupiter, using each encounter to build speed. It finally arrived at Saturn in July 2004, after nearly 7 years in flight. When it fired its engine for orbital insertion, scientists on Earth held their breath. For 96 tense minutes, they waited as the spacecraft vanished behind Saturn's disk. Then, one by one, the signals returned. Cassini was in orbit. From that moment, the study of Saturn entered a new age. The images that followed were breathtaking. Storm systems larger than Earth, hexagonal jet streams at the planet's north pole, shadows of moons cast across the rings like clockwork mechanisms. The planet's auroras shimmered in ultraviolet light, and Titan's surface began to reveal itself under radar. Lakes, rivers, and dunes of methane and ethane. For the next 13 years, Cassini would rewrite everything we knew about Saturn. It would show us that the rings rain ice onto the planet's atmosphere, that storms erupt with lightning more powerful than any on Earth, and that a tiny icy moon, Enceladus, is spewing water vapor into space from cracks in its crust. But those revelations lay ahead. In 1981, as Voyager 2 drifted beyond Saturn's gravitational pull, the last words transmitted from Mission Control captured the awe of the moment. "We are leaving the Lords of the Rings behind, but they will not leave us." Saturn had opened its arms, and humanity would return. Part 3. The moons of fire and ice beyond the brilliance of the gas giants. Hidden within their gravitational embrace lie some of the most extraordinary worlds in the solar system. When Voyager 1 and Voyager 2 passed through the Jovian and Saturnian systems, they revealed that the true wonders of these planets were not their swirling clouds or colossal storms, but the small, enigmatic moons that orbit them, worlds of fire and ice, heat and silence, destruction and creation. Each moon became a question in itself. How could these tiny bodies, so far from the warmth of the sun, possess the energy to reshape their own surfaces? How could there be motion or liquid or even chemistry in places where temperatures fall hundreds of degrees below zero? The answers would begin with one shocking discovery: a world alive with fire. It was March 1979 when Voyager 1 sent back the first images of Io, Jupiter's innermost Galilean moon. At first glance, it seemed alien even by cosmic standards, a sulfur-yellow sphere, pockmarked with strange circular features. But one long-exposure image captured something unexpected: a plume, rising high above the moon's limb. Scientists at the Jet Propulsion Laboratory thought it was an artifact, perhaps a camera error. But as the next sequence of photos arrived, the truth became undeniable. Io was erupting. Volcanoes, active, ferocious, and relentless, dotted its surface. Their plumes stretched hundreds of kilometers into space, falling back as frozen sulfur, snow. Io was not a dead rock. It was a world in turmoil. The source of that energy lay not within its core, but in its orbit. Trapped between the immense gravitational pulls of Jupiter, Europa, and Ganymede, Io was being stretched and squeezed with every revolution. The friction from this tidal flexing generated enormous heat, enough to melt rock into magma. It was the first time scientists had seen active volcanism beyond Earth. The discovery stunned geophysicists. Io proved that even in the deep cold of the outer solar system, energy could exist in abundance, not from sunlight, but from gravity itself. Just beyond Io's fiery orbit lay Europa, a moon of ice. Its surface gleamed smooth and bright, almost featureless except for long, intersecting cracks, lines that stretched for thousands of kilometers, resembling the pressure ridges of polar ice on Earth. To the cameras of Voyager 2, Europa looked deceptively simple. But those patterns told a hidden story. Something beneath the ice was moving. Decades later, when the Galileo spacecraft entered Jupiter's orbit in 1995, it confirmed what Voyager had only hinted. Europa's icy crust hides a global ocean, one that could be more than 100 kilometers deep. Its surface flexes under Jupiter's tidal pull, generating internal heat that keeps the ocean from freezing solid. The data suggested the presence of salts, minerals, and even possible thermal vents at the seafloor. In the quiet darkness beneath Europa's ice, the conditions could be similar to the hydrothermal vents of Earth's oceans, environments that, on our planet, teem with life. No sunlight, no photosynthesis, only chemistry and heat. The thought was both thrilling and unsettling. If life could arise in such a place, then perhaps biology is not the exception in the universe, but the rule. Farther out, in Saturn's domain, another small moon began to whisper its own secret. Enceladus, barely 500 kilometers wide, it had been almost overlooked by the Voyager missions. Its surface appeared unusually reflective, bright as fresh snow. When Cassini arrived in 2004 and began its survey, the magnetometer team noticed something odd. The planet's magnetic field wavered as the probe passed near Enceladus, as if the little moon were exhaling. A second flyby revealed the same anomaly. So Cassini's course was altered to make a daring, close pass, just 175 kilometers above the surface. What it found rewrote the textbooks. Jets of water vapor were erupting from giant fissures at Enceladus's south pole, fractures later named the Tiger Stripes. The plumes extended hundreds of kilometers into space, containing water, salts, and complex organic molecules. Beneath the crust, a warm global ocean churned in the dark. Gravitational squeezing by Saturn generated enough heat to keep that water liquid, and possibly to fuel hydrothermal activity. The implications were staggering. Here, far from the sun, in a place colder than Antarctica's deepest winter, there was liquid water, organic chemistry, and energy, the three fundamental ingredients of life. Enceladus became an instant priority for astrobiologists. The icy grains from its plumes even formed Saturn's faint outer earring, replenished continuously as if the moon itself were breathing. Suddenly, the search for life in the solar system no longer centered on Mars alone. While Cassini continued to orbit Saturn, attention shifted between Titan's thick atmosphere, Enceladus's hidden ocean, and the countless smaller moons that sculpted the planet's rings. Together, they formed a system of astonishing complexity, a miniature version of the solar system itself. Meanwhile, back at Jupiter, Galileo's observations were changing our understanding of the giant's magnetic environment. The radiation belts that once crippled Pioneer 10 were mapped in exquisite detail. Io's volcanic gases filled Jupiter's magnetosphere with charged particles, creating immense auroras that dwarfed Earth's. Europa, Ganymede, and Callisto interacted with these magnetic fields, generating their own miniature magnetospheres, invisible shields of plasma that pulsed with every orbit. Each moon was part of a vast electrical circuit powered by Jupiter's rotation, a cosmic machine of unimaginable scale. And in its heart, storms like the Great Red Spot spun for centuries without rest. To the scientists who followed these missions, the realization was profound. Planets were not isolated objects. They were systems alive with motion and exchange. Moons influenced planets, planets shaped moons. Everything in the solar system was bound by a single fabric of gravity, magnetism, and time. When Cassini dove through Enceladus's plumes again and again, 24 times in total, it gathered dust, ice, and vapor, analyzing them with onboard spectrometers. The results were astonishing. Alongside water and salt were traces of hydrogen and silica, substances that could only be produced by hot water reacting with rock. On Earth, that process occurs at hydrothermal vents, where chemical energy supports entire ecosystems. It was the closest thing yet to evidence that life, or something like it, might exist beyond our planet. The outer solar system, once thought to be a frozen wasteland, had revealed itself as a place of constant energy, of fire within ice. And just as scientists began to grasp the significance of these revelations, a new challenge was rising closer to home. The search for life on the red planet itself, a world where water once flowed, and where silence might conceal the echoes of an ancient biosphere. The next chapter of exploration would turn humanity's gaze inward again, toward Mars, the planet that had haunted our myths for millennia. Part 4. The red planet awakens. Mars has always been more than a world. It has been a mirror, a crimson reflection of human imagination. For centuries, the red planet inspired fear, longing, and the idea that we might not be alone. Ancient astronomers named it for the god of war, its blood-red hue a sign of celestial unrest. By the late 19th century, as telescopes improved, that unease turned to fascination. Astronomers claimed to see dark channels crisscrossing its surface, canals that some believed were built by intelligent life struggling to survive on a dying world. But by the dawn of the space age, those canals had vanished under scrutiny. Mars, it turned out, was dry and silent. Yet the question remained, had it always been that way? The first probes to reach for Mars were fragile emissaries launched into the unknown. In the 1960s, both the Soviet Union and the United States sent a series of robotic explorers toward the red planet. Most failed. Signals were lost, rockets misfired, or landers crashed. But in 1971, after years of attempts, NASA's Mariner 9 became the first spacecraft to orbit another planet. What it found changed everything. When Mariner 9 arrived, Mars was engulfed in a planet-wide dust storm. The surface was hidden beneath a swirling haze of red and brown. For weeks, scientists could only stare at featureless clouds. Then, as the dust began to settle, 3 massive peaks emerged above the storm, the summits of volcanoes taller than Mount Everest. One of them, Olympus Mons, dwarfed anything on Earth. The surface of Mars was not simply dead. It was scarred by colossal geological forces. Further mapping revealed vast canyons, dry riverbeds, and branching channels that looked unmistakably carved by flowing water. For the first time, scientists realized that Mars had once been a world of rivers and rain, its landscape molded by liquid. A few years later, in 1976, NASA's twin Viking missions took the next leap. Each consisted of an orbiter and a lander, designed not only to photograph the surface but to conduct biology experiments, the first direct search for life on another planet. Viking 1 and Viking 2 descended onto 2 different sites, Chryse Planitia and Utopia Planitia. As the first color images appeared on monitors at the Jet Propulsion Laboratory, the room fell silent. The Martian landscape stretched away in dusty reds and golden light, scattered with rocks and distant hills. For a moment, it looked hauntingly familiar, a desert not unlike those on Earth. The biology experiments were simple in principle, complex in execution. Each lander collected soil, added nutrients, and searched for signs of metabolism, chemical reactions that might suggest living microbes. The results were puzzling. One test produced positive results, but another contradicted it. The data could be explained by chemical reactions in the soil, not biology. In the end, NASA declared there was no clear evidence of life. The verdict was devastating for some, inconclusive for others. Carl Sagan, who had helped design the Viking cameras, called Mars a world that was once alive. Yet for the next 2 decades, the planet would remain largely untouched, its mysteries buried beneath its thin, pink sky. It wasn't until 1996 that a discovery on Earth reignited the debate. A meteorite, designated ALH 84001, found in Antarctica, was identified as a fragment ejected from Mars millions of years earlier. Inside it were microscopic shapes resembling fossilized bacteria. The announcement made global headlines. Had life once existed on Mars after all? Debate raged for years, and the scientific community remained divided. Still, the question could no longer be ignored. NASA responded with a new generation of missions, smaller, cheaper, faster. The Mars Global Surveyor launched in 1996, returning images so sharp that scientists could see details just a few meters across. It revealed layered sedimentary rock formations, proof that water had once pooled and evaporated repeatedly. Then, in 1997, came Mars Pathfinder and its tiny rover Sojourner. Using airbag technology to cushion its landing, Pathfinder touched down in a rocky plain known as Ares Vallis. When Sojourner rolled down its ramp and onto the Martian surface, it became the first robot to drive on another planet. The world watched live as its camera sent back images of boulders, dust, and distant hills. The mission lasted far longer than planned, proving that even small, low-cost probes could achieve scientific miracles. For the first time since Viking, Mars felt close again, reachable, tangible, alive. From orbit, the Mars Odyssey spacecraft continued the work, mapping the planet's surface composition and detecting hydrogen just below the soil, a signature of water ice. Then, in 2003, the European Space Agency entered the race with Mars Express. Though its lander, Beagle 2, failed to deploy, the orbiter revealed new mysteries. Methane and ammonia in the atmosphere, gases that degrade quickly in sunlight. Their presence implied an active source, perhaps geological, perhaps biological. By the early 2000s, Mars was no longer the barren wasteland of imagination. It was a planet that had once flowed with water, and maybe still concealed it beneath the surface. The question of life, ancient or present, had returned, stronger than ever. Then, in 2004, two rovers touched down, Spirit and Opportunity. They were designed to last 90 days. They survived for years. Rolling across dusty plains and crater rims, they found sedimentary rocks rich in minerals that form only in liquid water. Opportunity's cameras captured ripples in the soil that looked like those left by ancient waves. Mars, it seemed, had once been wet, very wet. When dust storms buried the rovers, they slept through the cold and awoke when the winds cleared their solar panels. For engineers at NASA, it was a quiet miracle, machines enduring far beyond their design, stubbornly alive in an alien world. Every discovery pointed to the same conclusion: Mars was once habitable. The only missing piece was proof of life, past or present. That search would define the next era of exploration. Larger, smarter rovers were already being built, equipped with laboratories capable of analyzing rock and soil at the atomic level. But even as we prepared to dig deeper into the red planet's secrets, we were still grappling with an older truth. The story of Mars is also the story of Earth. How planets live, change, and die. Mars had awakened. The next missions would determine whether it had ever truly lived. Part 5. Engines of Discovery. Every age of exploration is defined by its tools. The age of sail had its ships. The space age has its machines. In the void between planets, our ships are not of wood and canvas but of titanium, silicon, and plutonium. They do not ride the wind but the silent pressure of gravity and time. Each carries within it the distilled essence of human ingenuity. Engines that burn only once, sensors that will never be repaired, and instruments that must work perfectly hundreds of millions of kilometers from home. By the 1990s, the era of quick flybys was over. Scientists no longer wanted snapshots of the outer planets. They wanted residence, persistence, and intimacy. That ambition would give birth to a new generation of explorers: Galileo, Cassini, and Juno. The Galileo spacecraft began as a dream in the early 1980s. It was to be the first probe to orbit Jupiter, to stay long enough to witness its storms evolve and its moons breathe. But fate delayed it. The Challenger disaster in 1986 grounded the space shuttle fleet, and Galileo, already built, was stored away in silence for years. When it finally launched aboard Atlantis in 1989, it carried a revised flight plan. New safety restrictions meant the powerful booster it had been designed to use was banned. Instead, Galileo would take the long road, slingshotting around Venus and Earth twice before setting course for Jupiter. The voyage was not without drama. During its cruise, engineers attempted to deploy its massive 4.8-meter antenna, the umbrella-like structure that would allow high-speed data transmission across the solar system. It failed to open. For months, technicians at the Jet Propulsion Laboratory tried every command imaginable. Warming cycles, vibration bursts, even slow rotations of the entire spacecraft to shake it free. Nothing worked. The antenna was locked. That failure could have ended the mission. Instead, the team improvised. They rerouted data through a smaller, slower backup antenna, compressing information and rewriting software mid-flight. What was lost in speed was gained in ingenuity. As Galileo approached Jupiter in late 1995, it released a small atmospheric probe, a metal capsule the size of a piano, aimed directly at the planet's cloud tops. The probe entered the Jovian atmosphere at 170,000 kilometers per hour, enduring temperatures hotter than the surface of the Sun. For 61 minutes, it transmitted data as it fell: pressure, temperature, and composition. The results were startling. Jupiter's upper atmosphere contained far less water than expected and surprising amounts of helium and other trace gases. The planet was not the simple hydrogen giant scientists had imagined. It was a world of complex chemistry and deep heat. Meanwhile, Galileo itself fired its main engine for 49 minutes to enter orbit, an anxious eternity for engineers on Earth. When the signal confirming success finally arrived, humanity had achieved something extraordinary: a permanent artificial moon of Jupiter. For the next 8 years, Galileo orbited the giant world 35 times. It studied lightning storms that dwarfed continents, radiation belts powerful enough to destroy unprotected electronics, and a magnetic field so immense it could be detected millions of kilometers away. But its greatest legacy came from its encounters with Jupiter's moons. At Ganymede, Galileo discovered an intrinsic magnetic field, the only moon in the solar system known to have one, suggesting a molten metallic core. Europa's ice crust revealed the telltale signs of movement, cracking and shifting above a hidden ocean. Io's volcanic fury was captured in vivid detail, proving that tidal heating could power a world for billions of years. Even Callisto, pockmarked and ancient, held hints of subsurface water. The Galileo mission survived longer than anyone dared hope. Radiation battered its instruments, and memory tapes degraded. Engineers invented new code to help the onboard computer recover from random resets. It became a masterclass in remote problem-solving, a triumph of persistence and creativity. When its fuel finally ran low in 2003, NASA faced a dilemma. If Galileo were left adrift, it could one day crash into Europa, contaminating its pristine ocean with earthly microbes. The solution was both poetic and final. On September 21st, Galileo was commanded to dive into Jupiter's atmosphere. The probe burned like a meteor, becoming part of the planet it had studied for nearly a decade. Even before Galileo's fiery end, engineers were building its successor, a mission that would take everything learned from Jupiter and bring it to Saturn. That mission was Cassini. Launched in 1997, Cassini was an international masterpiece. NASA built the spacecraft, the European Space Agency contributed the Huygens lander, and Italy provided the high-gain antenna. It was the largest interplanetary probe ever constructed, weighing over 5 tons and carrying a dozen sophisticated instruments. Its journey to Saturn took 7 years and included 4 gravity assists: 2 from Venus, 1 from Earth, and 1 from Jupiter. Each flyby refined its trajectory with exquisite precision. In July 2004, Cassini fired its engines for more than an hour to enter orbit around Saturn. When the first images came in, they were beyond anything scientists had imagined. The rings were revealed not as static bands but as dynamic, living structures, waves, braids, and wakes sculpted by shepherd moons. Lightning storms raged across the planet's surface, each bolt stretching thousands of kilometers. 6 months later, Cassini released its small passenger, the Huygens probe. After a 3-week descent through Titan's atmosphere, Huygens landed softly on a frozen plain. Its cameras revealed an alien world shrouded in haze, with river channels and lakes carved not by water, but by liquid methane. Titan, it turned out, had weather, rain, clouds, and wind, operating in cycles eerily similar to Earth's, but with entirely different chemistry. While Huygens transmitted for only a few hours, Cassini remained in orbit for 13 years, looping around Saturn in intricate patterns that brought it close to dozens of moons. It discovered that Enceladus, the tiny moon once thought unremarkable, was venting water vapor and organic molecules into space from cracks near its south pole. The data pointed to a warm ocean beneath the ice, an ocean that could harbor life. In its final year, Cassini performed a breathtaking series of dives through the gap between Saturn and its innermost ring, sampling the planet's atmosphere and measuring the flow of ring rain, fine particles of ice and dust falling into Saturn like snow. On September 15, 2017, with its fuel nearly gone, the spacecraft plunged into the atmosphere and disintegrated, its signal fading into static. The mission had lasted nearly 20 years. But the story of planetary exploration did not end there. A new kind of spacecraft was being built, one that would return to Jupiter with a different goal, to study the planet itself, not just its moons. That mission was Juno. Launched in 2011, Juno was a paradox, both advanced and minimalist. It relied not on nuclear power but on vast solar panels, a daring choice given that Jupiter receives only 4% of the sunlight Earth does. Inside its body, the probe's computers were encased in a thick titanium vault to shield them from radiation. Its trajectory carried it past Earth for a final gravitational boost, flinging it toward the giant planet at 250,000 kilometers per hour. When Juno entered orbit on July 4, 2016, it became the closest observer of Jupiter in history. Its polar trajectory allowed it to peer over the planet's north and south poles, regions never before seen. What it found defied expectations. Beneath the clouds, the atmosphere churned with cyclones arranged in near-perfect geometric patterns. The Great Red Spot extended hundreds of kilometers deeper than previously imagined, and the magnetic field was not symmetrical but lumpy, as if generated by processes we barely understand. Juno revealed Jupiter not as a simple gas sphere but as a planet of profound complexity, a machine of storms and magnetism, possibly shaped by remnants of the early solar system itself. Through Galileo, Cassini, and Juno, humanity learned that exploration is not a race but a dialogue between what we know and what we dare to ask. Each mission carried within it lessons for the next: how to survive radiation, how to navigate gravity, how to listen to the faintest whispers from the void. They were not just machines. They were the engines of discovery, and through them, we were beginning to see the solar system not as a collection of separate worlds, but as one great interwoven story. Part 6. Echoes of a living solar system. Every new image from deep space tells a story, but rarely just about the world it depicts. Often, it tells us something about our own planet, about what we are made of, and how fragile life's balance truly is. As the great missions of the late 20th and early 21st centuries, Galileo, Cassini, Juno, Spirit, Opportunity, sent back their data, a remarkable pattern began to emerge. It was as if the solar system itself were whispering a single message: everything is connected. For centuries, humanity had imagined the planets as isolated islands, each obeying its own laws. Mercury burned, Venus suffocated, Earth thrived, Mars froze. The giants beyond were cold, silent sentinels. But with every passing mission, that old view crumbled. What we discovered instead was a solar system alive with motion and exchange, where heat, magnetism, and chemistry flow between worlds. On Jupiter, the Juno spacecraft revealed that storms behave less like weather systems and more like living organisms, growing, dividing, and merging in ways that defy prediction. At Saturn, Cassini watched the planet's rings shed their material into the upper atmosphere, ring rain, that changed its chemical makeup day by day. Even in the frozen depths of the outer system, tiny moons like Enceladus and Europa pumped water vapor into space, feeding vast halos of gas and dust around their parent planets. It was an astonishing realization. The solar system was not static. It breathed. Scientists began to see it as a dynamic, interconnected system, one that might even have feedback loops like those of a living body. Moons influenced planetary magnetospheres. Magnetospheres shaped atmospheres, and gravity linked them all together in a constant rhythm of motion. Nowhere was that interconnection more profound than in the search for life. The discovery of oceans beneath the ice of Europa and Enceladus reframed one of science's oldest questions. Does life require sunlight? On Earth, the first living organisms may have emerged around hydrothermal vents, places where sunlight never reached, and yet chemistry flourished in the dark. If the same conditions exist on those distant moons, could life be there as well? Not intelligent life, perhaps, but microbial, resilient, and ancient. To answer that question, scientists began to examine not just where water exists, but how energy flows. On Europa, tidal flexing from Jupiter's gravity produces internal heat, melting the ice from below. On Enceladus, friction and chemical reactions between rock and water generate hydrogen gas, a potential energy source for microbes. Even on Mars, the discovery of recurring slope lineae, dark streaks that appear seasonally on crater walls, hinted that salty liquid water might still seep across its surface today. These findings forced scientists to rethink the definition of a habitable zone. Traditionally, it was a narrow band around a star where temperatures allowed liquid water to exist on a planet's surface. Earth was comfortably inside it. Mars lay near its edge. But now the rules were changing. Worlds far outside that golden zone, icy moons orbiting frozen giants, might host entire ecosystems beneath their shells. Life, it seemed, could exist in the most improbable corners of the cosmos. The discoveries also reshaped our understanding of how planets themselves evolve. Cassini's data showed that Saturn's rings, long thought to be as old as the planet, might actually be young, perhaps only a few 100 million years old, born from a shattered moon or captured comet. Juno's gravity measurements revealed that Jupiter's core might not be solid at all, but a vast region of metallic hydrogen blending gradually into the planet's interior. Mars, once thought geologically dead, displayed traces of recent seismic activity, subtle Marsquakes that hinted at a restless interior. Everywhere we looked, the solar system seemed to pulse with change. Even the Sun, long considered a steady beacon, revealed new complexity. Its magnetic storms reached across billions of kilometers, influencing the atmospheres of planets and the orbits of dust. Radiation from solar flares could strip atmospheres or ignite auroras. In a very real sense, the entire solar system was part of a single machine, one engine of energy and motion driven by the heartbeat of our star. This realization transformed planetary science into something deeper, almost ecological. To understand Mars, one had to study Earth. To explain Jupiter, one had to model the Sun. The boundaries between astronomy, geology, and biology began to blur. Scientists coined a new term for this cross-disciplinary frontier: astrobiology, the study of life as a cosmic phenomenon. For astrobiologists, the solar system became a laboratory, a set of experiments billions of years in the making. Mars showed how a once wet planet could dry and freeze. Venus revealed how a runaway greenhouse effect could smother a world. Earth, still vibrant, became the control variable, the one place where life had survived. And the icy moons offered the tantalizing possibility that life might thrive even in darkness. Across the agencies NASA, ESA, JAXA, Roscosmos, ISRO, new missions were designed with these questions in mind. The Europa Clipper, set to launch in the 2020s, would carry radar to probe the moon's subsurface ocean. The JUICE mission, Jupiter Icy Moons Explorer, from the European Space Agency would target Ganymede, Callisto, and Europa. Plans for future landers on Enceladus were already being discussed. Probes that might fly directly through the plumes and analyze them for signs of biological molecules. Meanwhile, on Mars, Curiosity and Perseverance continued their long roving campaigns. Curiosity found evidence of ancient lakes and sediments rich in organic carbon, while Perseverance began collecting rock samples to be returned to Earth, the first attempt to bring pieces of another planet home for direct study. Each mission built upon the last, their discoveries weaving into a single narrative, the story of a living solar system. It was becoming harder to draw the line between life and its environment. Every planet, every moon seemed to participate in the same grand experiment. Energy moved, matter cycled, time sculpted. Even in the silence of space, there was motion, exchange, and memory. As scientists pieced together this new cosmic ecology, one conclusion began to form: quiet, humbling, and beautiful. Life might not be the anomaly of the universe. It might be one of its natural expressions. Part 7. Signals from the past. Every spacecraft that leaves Earth carries with it more than instruments and sensors. It carries a time machine. Each transmission, each spectrum of light is a signal from the past, a clue to how the solar system began. As the data from Juno, Cassini, Galileo, and the Mars rovers accumulated, a new question rose above all others. Where did all this begin? The answer, scientists suspected, was buried in the chemistry of the worlds themselves. By studying their atmospheres, their rocks, and even their magnetic fields, we could rewind the clock 4.5 billion years, to a time when the sun was still surrounded by a swirling disk of dust and gas. In that ancient era, chaos reigned. Dust grains collided and clumped together, forming planetesimals, the seeds of planets. Hydrogen and helium collected in vast envelopes around the largest of these, giving birth to the gas giants. Meanwhile, closer to the sun, lighter gases were stripped away, leaving behind rocky planets like Earth and Mars. But there was a mystery. How did the inner planets, including our own, acquire water and organic molecules, the essential ingredients for life? For decades, theories abounded. Some scientists believed comets, icy remnants from the solar system's outer regions, had delivered water during a violent bombardment billions of years ago. Others argued that asteroids, not comets, carried the right isotopic signatures. The truth, it seemed, was not so simple. When Rosetta, the European Space Agency's comet-chasing mission, rendezvoused with Comet 67P/Churyumov-Gerasimenko in 2014, it sampled water vapor from its surface. The ratio of hydrogen isotopes didn't match Earth's oceans. Comets like 67P couldn't have been the main source of our water. But meteorites, fragments of ancient asteroids, did show matching isotopic ratios. Perhaps Earth's oceans had been seeded by rocky messengers from the asteroid belt, not by icy wanderers from deep space. Yet even that story was incomplete. Cassini's instruments detected complex organic molecules, the building blocks of life, within the plumes of Enceladus and the atmosphere of Titan. On Mars, Curiosity drilled into ancient mudstone and found traces of carbon compounds older than any terrestrial fossil. On Comet 67P, Rosetta found glycine, one of the amino acids used in the proteins of living organisms. Everywhere we looked, the signature of organic chemistry appeared. It was as if the universe itself had been generous, scattering the ingredients of life like seeds across the solar system. One of the most surprising insights came from Jupiter. Juno's instruments revealed that the planet's atmosphere held an unexpected abundance of heavy elements: oxygen, nitrogen, carbon, suggesting that Jupiter had swallowed countless icy planetesimals during its formation. This supported a new model, that Jupiter's migration through the early solar system may have stirred the cosmic disk, mixing materials from distant regions and distributing water-rich debris toward the inner planets. In other words, we owe our oceans to Jupiter's wandering. The story of the solar system, it turned out, was one of movement, not stability. Planets had migrated, moons had shifted, orbits had changed. The delicate clockwork we see today was not how it began. Over time, gravitational resonances between Jupiter and Saturn had sculpted the asteroid belt, sending comets inward and reshaping the destinies of smaller worlds. Even Mars bore scars of this ancient turbulence. Its thin atmosphere and frozen deserts are remnants of a once active climate that vanished when the planet lost its magnetic field. Without protection, the solar wind stripped away its air, leaving behind the oxidized dust that gives Mars its distinctive hue. Yet deep beneath the surface, frozen reservoirs of water ice remain, a geological memory of a world that once had oceans and rain. On Earth, we see echoes of that same story in our rocks and fossils. Zircons older than 4 billion years show evidence that liquid water existed on our planet almost immediately after its formation. That means the conditions for life arose astonishingly early, perhaps too early to be coincidence. If water and organics were so common, perhaps life was not a rare event, but a natural consequence of planetary chemistry. These revelations reshaped more than astronomy. They redefined humanity's place in the cosmos. For the first time, the story of life could be traced back not to Earth alone, but to the formation of the solar system itself. As the 20th century faded into the 21st, new generations of scientists began to speak of cosmic ancestry, the idea that life's ingredients were born in the hearts of stars, scattered by supernovae, and gathered again in worlds like ours. Every molecule of carbon, nitrogen, and oxygen in our bodies was forged in an earlier generation of suns. When we study the planets, we are studying the story of our own creation. The missions of the last 50 years, Voyager, Pioneer, Galileo, Cassini, Juno, Curiosity, Rosetta, were not just expeditions of exploration. They were acts of remembrance, collecting the fragments of our origin from the silence of space. And yet, for all our understanding, one question still lingers like a distant signal. If life's ingredients are everywhere, if oceans and chemistry abound, where is everyone else? That question, the paradox of life's apparent absence in a universe filled with possibilities, would soon become the next great inquiry. It would drive not only new missions, but a new philosophy of exploration. Because the search for life is not just a scientific pursuit. It is, in the end, a search for meaning. Part 8. The great silence. For all our listening, for all our wandering machines, the universe has remained silent. No messages, no signals, no evidence of intelligence beyond Earth. And yet, everywhere we look, the ingredients for life abound. Oceans beneath icy crusts, carbon compounds in the dust of comets, methane in the skies of distant planets. It is the most haunting paradox of all. If life is common, where is everyone? This question, known as the Fermi paradox, has followed humanity since the dawn of the space age. In the 1950s, physicist Enrico Fermi famously asked, during a casual lunch conversation, "Where is everybody?" It was a simple question with devastating implications. By all logic, if life can arise easily, if intelligence and technology are natural extensions of evolution, then the galaxy should be teeming with civilizations. And yet, as our telescopes scanned the stars and our probes explored the planets, the silence persisted. When Voyager 1 left the solar system in 2012, it carried with it the golden record, a copper disk etched with sounds and images of Earth, greetings in 55 languages, the cry of a baby, the hum of wind, the laughter of children. The record was not just a message, it was a gesture, a way of saying we are here. But in the decades that followed, nothing answered. The first great listening efforts began in the 1960s, when astronomer Frank Drake pointed a radio telescope toward two nearby sun-like stars. His experiment, called Project Ozma, was simple: listen for narrowband radio signals that could not be produced by nature. There was no response, but the experiment ignited a movement. In the decades that followed, SETI, the search for extraterrestrial intelligence, grew from a fringe idea into a disciplined science. By the late 20th century, advances in computing allowed telescopes to scan millions of frequencies simultaneously. The Arecibo Observatory, with its giant 305-meter dish nestled in a Puerto Rican valley, became humanity's greatest ear. It listened to the sky day and night, searching for whispers among the cosmic static. In 1974, Arecibo transmitted a message of its own, a binary signal sent toward a distant star cluster 25,000 light-years away. The The message contained information about human biology, our solar system, and the structure of DNA. Scientists knew it would take 50,000 years to get a reply, but the act itself mattered. It marked the moment when Earth deliberately announced itself to the galaxy. Meanwhile, our robotic emissaries Pioneer 10, Voyager 1 and 2, New Horizons, carried similar messages physically, inscribed on plaques and records. They were not just scientific missions, they were ambassadors. Still, the silence continued. Astronomers began to wonder if we were looking or listening in the wrong way. Perhaps alien civilizations used technologies beyond our imagination. Lasers, neutrino beams, quantum communications, or methods that required no electromagnetic signals at all. Or perhaps they simply chose not to speak. Some proposed darker answers. Maybe intelligence always destroys itself before it can spread, through war, exhaustion, or technological collapse. Others suggested that life is rare not because it cannot arise, but because it rarely survives. Yet, as the pessimism grew, so did the data. The Kepler Space Telescope, launched in 2009, revealed thousands of exoplanets orbiting distant stars, many of them roughly Earth-sized, many in the so-called habitable zone. What had once seemed improbable, that planets are common, became an established fact. The Milky Way alone might hold tens of billions of potentially habitable worlds. If even a fraction of them host life, then the silence becomes more profound. SETI researchers began to shift their focus. Instead of listening for deliberate transmissions, they started searching for technosignatures, indirect evidence of advanced activity, artificial light on a planet's night side, waste heat from megastructures, unusual patterns in starlight that could indicate massive orbital engineering. One such anomaly briefly captured global attention in 2015, when astronomers noticed a regular dimming in a star known as KIC 846-2852, nicknamed Tabby's star. The brightness fluctuated unpredictably, leading some to speculate wildly about alien megastructures. The excitement was short-lived. Later analysis pointed to clouds of dust. But the event highlighted how hungry humanity had become for any hint of cosmic company. Meanwhile, our own probes continued to listen in their own way. Juno, orbiting Jupiter, studied radio emissions from the planet's auroras. Cassini heard the whisper of plasma waves within Saturn's magnetosphere eerie, musical sounds produced by charged particles. Even Voyager 1, now billions of kilometers away, detected faint ripples in the interstellar medium, proof that space itself hums with energy. Perhaps, some suggested, the silence isn't truly silent. Maybe we just haven't learned to understand the language. As artificial intelligence grew more sophisticated, new algorithms began analyzing the mountains of SETI data that had lain dormant for years. Machine learning detected signals once dismissed as noise. In 2023, one such algorithm found 8 unexplained narrowband emissions, all likely natural but proof that we were improving our hearing. Even so, the paradox endures. The universe seems eager for life, but reluctant to show it. Some scientists take comfort in this. They argue that the absence of evidence is not evidence of absence, that the cosmos is vast, and our search has barely begun. Others find the silence more troubling, suggesting that we may indeed be the first or the last. And yet, amid that silence, humanity keeps sending its messengers outward. Voyager 1 continues to drift through interstellar space, its weak signal still reaching Earth. Pioneer 10, long silent, sails on beyond the reach of our detectors. New Horizons, now past Pluto, carries the ashes of Clyde Tombaugh, the man who discovered that distant world, into the dark. Each of them moves at tens of thousands of kilometers per hour, yet the nearest star remains tens of thousands of years away. We will not live to know where they go, or if they will ever be found. But that is not the point. The act of sending them, of listening, of hoping, is the clearest expression of what it means to be human. Because the great silence is not a void. It is an invitation. An invitation to keep searching, to keep asking, to keep believing that somewhere, beyond the noise of stars and the whisper of cosmic radiation, another voice might be waiting to answer. Part 9. The Age of Collaboration. By the dawn of the 21st century, a quiet transformation had begun. Space was no longer the domain of rivalry, it was becoming a shared endeavor. The Cold War had ended, and with it, the notion that exploration must be a race between nations. Instead, the exploration of the cosmos began to resemble what it had always been in spirit. A collective pursuit of knowledge, transcending borders, languages, and politics. Humanity, at last, was beginning to act like a single civilization looking outward. The seeds of this cooperation had been planted decades earlier. The International Space Station, a joint effort between the United States, Russia, Europe, Japan, and Canada, served as a model for what planetary science could become. A platform where scientists worked side by side, orbiting above the divisions of Earth. In its laboratories, experiments on microgravity, radiation, and biological resilience quietly laid the groundwork for deep space exploration. But it was in the robotic missions, the emissaries sent to the outer worlds, that international collaboration truly flourished. Cassini, launched in 1997, had been the first major planetary mission built on a foundation of global partnership. NASA provided the spacecraft, the European Space Agency contributed the Huygens lander, and the Italian Space Agency designed the communication antenna. It was an alliance of engineering, trust, and shared ambition, and it became one of the most successful planetary missions in history. After Cassini's triumph, cooperation became the new standard. The European Space Agency's Mars Express mission, launched in 2003, carried instruments built by scientists from 15 countries. Japan's Hayabusa and Hayabusa 2 missions pioneered sample return technology from asteroids, sharing data with NASA and ESA teams. India's Mars Orbiter mission, launched in 2013, became a point of pride not just for its home nation but for a planet learning to explore together, an achievement that demonstrated deep space navigation could be done on modest budgets with extraordinary precision. Even China, once isolated in its own program, began to contribute to the new era. The Chang'e Lunar Series and Tianwen-1 mission to Mars expanded the network of exploration, adding data, redundancy, and diversity of perspective. For scientists, these missions were not just political milestones. They represented a practical truth. The solar system is vast, and no single nation can explore it alone. The same cooperative spirit extended to the search for life. The upcoming Europa Clipper, built by NASA, would coordinate with the European Space Agency's JUICE, Jupiter Icy Moons Explorer, to study Jupiter's moons in concert, 2 spacecraft, from 2 agencies, sharing one scientific vision. JUICE would focus on Ganymede, Callisto, and the larger Jovian environment, while Europa Clipper would dive repeatedly through Europa's thin atmosphere, scanning for organic molecules and chemical signatures of habitability. Together, they would build a complete portrait of the Jovian system, something no single mission could achieve. Collaboration also reshaped how we understood data. In the past, mission archives were proprietary, often restricted to national agencies or closed research groups. Now, planetary science began to embrace openness. NASA's Planetary Data System, ESA's Science Archives, and similar repositories worldwide became public, allowing anyone, from professional astronomers to high school students, to explore the raw images and spectra of other worlds. In this sense, exploration became democratized. The solar system belonged to everyone. This shift in philosophy was not purely altruistic. The challenges of planetary exploration, communication across billions of kilometers, extreme temperatures, radiation, and the physics of orbital mechanics, demanded a diversity of thought. One nation's limitations could be another's innovation. Where one agency had funding, another had expertise. Collaboration made missions possible that otherwise would never have left the blueprint stage. The technology reflected this merging of minds. The James Webb Space Telescope, built through cooperation between NASA, ESA, and the Canadian Space Agency, became the most powerful window into the cosmos ever created. Though designed primarily for astrophysics, its deep-field observations of exoplanets blurred the boundary between astronomy and planetary science. For the first time, Scientists could analyze the atmospheres of worlds around distant stars, detecting water vapor, carbon dioxide, and even methane. It was as if our robotic explorers, once confined to the solar system, were teaching us how to extend our curiosity to other suns. Meanwhile, Earth itself began to take on new meaning. The very data used to study Mars, Venus, and Titan was turned inward. By comparing planetary atmospheres, scientists gained fresh insights into our own climate system. Venus, once Earth's twin, had become a cautionary tale of runaway greenhouse effect. Mars, now frozen, showed what happens when a planet loses its atmosphere and magnetic field. Earth, sitting delicately between them, seemed more fragile than ever. For the first time, planetary science became a mirror not just of discovery but of responsibility. As spacefaring nations and private entities planned future missions to asteroids, to Europa, to Mars, questions arose not only about what we could do, but what we should do. Could we send landers to potentially habitable moons without contaminating them? What obligations did we have to protect alien ecosystems that might exist beneath the ice? Should humans set foot on Mars before we know what lives there, if anything at all? These were no longer speculative debates. The line between exploration and interference had grown thin. Planetary protection, once a bureaucratic term, became an ethical frontier. Out of this new era of cooperation and reflection emerged something even more profound, a sense of planetary unity. The image of Earth from space, once rare, was now routine. But repetition did not diminish its power. Each time a probe turned its camera back toward home, from the Moon, from Mars, from Saturn, it reminded us of who we are, one species, sharing one world under one fragile atmosphere. The farther we traveled, the clearer that truth became. The cosmos did not recognize borders. Gravity did not care for politics. And in the silence of space, collaboration was not just noble, it was necessary. In this age of shared discovery, exploration had become a conversation between nations, generations, and worlds. And that conversation was about to reach its most daring phase yet, when humanity began not only to explore, but to plan for its eventual presence among the planets themselves. Part 10. The path to presence. For centuries, humanity had watched the planets from afar, distant lights in the sky, then worlds captured in grainy black and white, and finally, in breathtaking color. But by the early decades of the 21st century, the age of observation was giving way to something even bolder, the age of presence. We were no longer content to send machines that merely touched, sampled, and vanished. The question was no longer, can we go there? It had become, when do we stay? This change did not happen suddenly. It began with the Moon, the first world humanity ever touched. The Apollo missions of the 1960s and 1970s had been acts of audacity, fueled by political urgency and national pride. 12 humans walked its surface, planted flags, and gathered rocks that would reveal the Moon's ancient history. But once the race was won, the engines cooled, and the silence returned. For decades, the Moon hung above us, untouched by human hands. Then, a new generation began to dream again. The 21st century's space ambitions were not born in the fire of rivalry, but in the pursuit of permanence. NASA's Artemis program, unveiled in the late 2010s, set an audacious goal: to return humans to the Moon, this time to stay. The mission would establish a sustainable base at the lunar South Pole, where sunlight lingers for months and water ice lies frozen in shadowed craters. Water meant air to breathe, fuel to burn, and life to sustain. This was not the Cold War's one-time spectacle. Artemis was the first step in a chain of continuity, a blueprint for how humans might live beyond Earth. Around the Moon, NASA and its international partners began planning the Lunar Gateway, a small, crew-tended space station that would orbit the Moon like a cosmic harbor. It would serve as a testing ground for long-duration missions, the bridge between worlds. But even as the Moon called us back, the red planet beckoned. For as long as we have gazed at Mars, it has seemed almost within reach, familiar yet untamed, desolate yet strangely inviting. Its day is just 40 minutes longer than ours. Its polar caps expand and recede with the seasons. It is the world most like Earth, and yet profoundly alien. To walk on Mars would be to step into a mirror of our planet's past, or its possible future. The idea of sending humans there was no longer science fiction. It was a logistical puzzle, one humanity was beginning to solve. The challenges were immense. The journey would take 6 to 9 months. Radiation exposure could be lethal, and communication delays would stretch up to 20 minutes each way. A crew on Mars would be on their own, unable to rely on instant guidance from Earth. Still, the technology was advancing. Spacecraft like SpaceX's Starship, NASA's Orion, and China's heavy-lift Long March 9 represented a new era of capability. Reusable rockets made access to orbit cheaper and more frequent. Private companies began to work hand in hand with government agencies, blurring the line between state and enterprise. For the first time since the dawn of the space age, humanity was building a transportation network between worlds. Yet going to Mars would not just be a triumph of engineering. It would be a test of endurance, psychological, biological, and ethical. The first settlers would face isolation, radiation, and the slow reshaping of their bodies under 1/3 gravity. The Martian dust, fine as powder and sharp as glass, could corrode machinery and harm lungs. Even water, though frozen in abundance beneath the soil, would require intricate systems to extract and purify. To prepare, analog habitats sprang up across Earth. In the deserts of Utah, the volcanic plains of Hawaii, the frozen plateaus of Antarctica. Here, volunteers lived for months in confinement, simulating the challenges of a Mars mission. Their experiences revealed what the data could not. That survival on another planet would depend as much on psychology and teamwork as on technology. Still, the vision persisted, because in every era of exploration, the destination has mattered less than the act of going. Humanity has always been defined by its urge to step beyond boundaries, oceans, mountains, or atmospheres. The leap to Mars, like the voyages of our robotic precursors, would be another chapter in that same story. The philosophical questions, however, deepened. What would it mean for humans to live, and perhaps die, on another world? Would Mars settlers see themselves as citizens of Earth, or of a new planet? Would the line between explorer and colonizer blur, as it had so many times before in human history? And what responsibility would we bear toward any possible native life, microbial or otherwise, that might exist there? Planetary protection was no longer a theoretical concept. It became a moral imperative. International agreements, like the Outer Space Treaty of 1967, prohibited claims of sovereignty in space and mandated the avoidance of harmful contamination of other worlds. But as plans for human bases solidified, the gaps in these laws grew visible. Could humans live on Mars without irreversibly altering it? Could we explore and preserve at once? Some argued that contamination was inevitable, that exploration itself is a form of transformation. Others countered that Mars, and every other world, has intrinsic value beyond our utility. In this tension, a new philosophy emerged: planetary stewardship. The idea that to explore the cosmos responsibly, humanity must treat every world, living or dead, as part of a shared cosmic heritage. While debates continued, progress advanced. The Perseverance rover, working alongside the small helicopter Ingenuity, demonstrated flight in the thin Martian atmosphere, the first powered flight on another planet. The Mars Sample Return Project, jointly led by NASA and ESA, aimed to bring back pieces of the planet for the first time. And in the background, quiet but relentless, engineers tested the technologies of life support, radiation shielding, and sustainable habitats that would one day carry humans farther than ever before. Each experiment, each launch, each line of code written for a robot on another world brought us one step closer to a profound threshold, the moment when humans would cease to be confined to a single planet. The path to presence was no longer science fiction. It was a matter of will, collaboration, and time. And as our machines paved the way across the void, one truth became clear: The story of exploration was transforming into the story of migration. For when we take our first steps on Mars, we will not simply be visiting. We will be expanding the definition of home. Part 11: Worlds Within Worlds. As humanity prepared to plant its first footprints on new soil, a deeper transformation began to unfold, not in the rockets or habitats, but in the way we thought about ourselves. For thousands of years, we had seen Earth as the center of our story, the cradle and limit of life. Now, for the first time, that cradle was opening. The solar system, once a collection of distant lights, was becoming a network of destinations. This was not just exploration anymore. It was evolution. The Moon, Mars, and the asteroids were no longer symbols of unreachable mystery. They were becoming economic and ecological extensions of Earth's sphere of influence. Private companies, universities, and national agencies alike began to imagine a solar economy, one in which resources, energy, and even human presence flowed between worlds. It began, as revolutions often do, with small steps. Private rockets, once dismissed as fantasy, were now launching payloads more frequently than governments ever had. Reusable boosters landed upright on drone ships, reducing the cost of reaching orbit by orders of magnitude. Satellites assembled in low Earth orbit formed constellations that connected the planet in ways once reserved for science fiction. Space, once a playground for superpowers, had become a marketplace of minds. Yet beneath the economics lay a quieter revolution, the redefinition of what world meant. For centuries, humans had imagined planets as separate entities, divided by distance and purpose. But as data from Cassini, Juno, Curiosity, and countless others poured in, that boundary blurred. Each planet was a laboratory, each moon a case study in climate, chemistry, and change. Humanity's lens widened. We were no longer studying the planets, but the patterns that linked them. That idea that every world is part of a continuum reshaped not only planetary science but philosophy itself. Venus became the archetype of greenhouse catastrophe, its carbon-choked atmosphere a glimpse into one possible future for Earth. Mars showed what happens when a planet loses its magnetic shield and atmosphere, drying into silence. Titan demonstrated how complex organic chemistry can emerge even in the freezing dark. And Europa and Enceladus, with their hidden oceans, proved that life's potential might not depend on sunlight at all. Each world was a version of a possible Earth. Each was a mirror. Back home, these revelations began to echo in classrooms, laboratories, and art studios. The concept of Earth system science, once limited to geology and meteorology, evolved into something far larger. Our planet was no longer studied in isolation but as one participant in a family of worlds governed by shared physics and cosmic history. This worldview inspired a new generation, one that saw environmental stewardship not as a burden, but as preparation. The technologies developed for sustaining life on Mars, closed-loop water systems, renewable energy, radiation shielding, and resource recycling, found applications on Earth's deserts, oceans, and cities. As humanity learned how to live sustainably on other planets, we began, at last, to learn how to live sustainably on our own. But with this expansion came ethical complexity. As private industry entered the stage, with companies planning asteroid mining, lunar construction, and even orbital tourism, new questions emerged. Who owns the moon? Who profits from Martian resources? Can we claim something that belongs to no one or to everyone? International treaties, drafted decades earlier, offered little clarity. The Outer Space Treaty of 1967 declared space the province of all humankind, but never defined what that meant in practice. Could a corporation extract minerals from the moon without claiming sovereignty? Could a settlement on Mars establish its own laws, or would it fall under terrestrial jurisdiction? Philosophers, lawyers, and scientists began to debate a new concept: cosmic commons, the idea that space and all celestial bodies are a shared inheritance of the human species. Under this view, exploration was not an act of ownership but of stewardship. We were not conquerors of the cosmos, but caretakers. And yet, ambition is rarely bound by ethics alone. The lure of resources, rare metals, solar energy, new frontiers of innovation, was irresistible. Asteroids, rich in platinum and nickel, represented trillions of dollars in potential value. Companies and space agencies drew up plans to capture, mine, and process them. What had once been myth, Prometheus stealing fire from the gods, was becoming an engineering problem. Meanwhile, the cultural implications of our expanding reach rippled through art, religion, and philosophy. The idea of being a citizen of Earth was evolving into something larger, a citizen of the solar system. Poets spoke of humanity's next horizon. Filmmakers and writers envisioned futures where Mars-born children looked back at Earth as the mythic old world. But beneath the romance of expansion lay an undeniable truth. The more worlds we touched, the more fragile our origins seemed. Every image of a cratered moon, every dusty Martian valley, was a reminder of how rare a place like Earth truly is. A planet where the balance between chaos and stability, light and shadow, allowed life to thrive. This awareness, paradoxically, deepened our sense of unity. As we reached outward, we began to see inward more clearly. The boundaries between nations, races, and creeds dissolved under the reality that beyond our thin atmosphere lay an infinite cold. The divisions that had once driven our conflicts seemed petty against the backdrop of the cosmos. A new narrative began to form, one that transcended conquest or competition. Humanity was no longer a species of a single world. We were becoming a civilization of many worlds, and in that realization lay both wonder and weight. For if we could expand across the solar system, we could also carry our mistakes with us. The exploitation of resources, the scars of pollution, the inequities of wealth, these patterns would not vanish in space. They would follow us unless we chose differently. To live among the planets would require not just technology, but wisdom. The worlds within worlds, Earth, Mars, Europa, Titan, were not prizes to be claimed. They were chapters in the same cosmic story, each one asking us to remember where we came from and to imagine what kind of civilization we wish to become. And even as we prepared to inhabit these new frontiers, one great question still loomed. What would come next? When the solar system was no longer a mystery, when our machines and our descendants roamed freely among its moons and rings, would we stop? Or would we look beyond, toward the stars themselves? Part 12. Crossing the dark at the edge of our solar system. Beyond the orbits of Neptune and Pluto, sunlight fades to a dim whisper. Temperatures drop toward absolute zero. The sun becomes just another bright star in the black. Yet even here, in this region of frozen silence, human presence endures. A handful of machines, tiny, tireless, and eternal, continue to move outward. Voyager 1 was the first to cross that boundary. In August 2012, more than 18 billion kilometers from Earth, it slipped through the invisible membrane separating the heliosphere, the bubble of charged particles streaming from the Sun, from the vast interstellar medium beyond. For the first time, a human-made object entered true interstellar space. Its radio signal, faint as a whisper, took over 17 hours to reach Earth. On that day, humanity became an interstellar species, if only through its machines. Behind Voyager 1, Voyager 2 followed, crossing its own boundary in 2018. Pioneer 10, Pioneer 11, and New Horizons trailed behind, bound for the same infinite dark. None would ever return. Yet each carried something priceless, a record of who we were, the sounds of Earth, the language of atoms, the coordinates of our sun. They are our first true messengers to the galaxy. For scientists and dreamers alike, these silent travelers represent the beginning of a new era, the interstellar age. But crossing the dark is not only a feat of distance. It is a transformation of thought. For centuries, our imagination stopped at the edges of the solar system. Beyond Neptune lay myth, the endless unknown. Now, technology is catching up to imagination. The same drive that carried us to the Moon, Mars, and the outer giants is beginning to focus on what lies beyond. Interstellar travel, once the realm of fiction, is slowly becoming a problem of physics and engineering. Projects like Breakthrough Starshot propose using ground-based lasers to propel tiny, wafer-thin probes to nearby stars at 20% the speed of light. In theory, such craft could reach the Alpha Centauri system, our closest stellar neighbor, in just over 2 decades. Each probe, no larger than a postage stamp, would carry cameras, sensors, and communication chips, powered by sunlight and laser energy. The technology is embryonic, but the principle is sound. Use light itself as propulsion. Other ideas draw on nuclear fusion, antimatter, or even the curvature of spacetime itself. Theoretical physicists debate the feasibility of warp drives, spacetime distortions that could move a vessel faster than light without violating relativity. For now, these remain mathematical dreams, but every great voyage begins as one. Still, distance is not the only obstacle. Time is the greater one. Even traveling at 1/10 the speed of light, a journey to the nearest star would take 40 years. To reach the center of the galaxy would take tens of thousands. The challenge of interstellar travel is, in essence, the challenge of patience, of how to sustain not just machines but meaning across centuries. That realization has begun to reshape humanity's idea of exploration. Instead of thinking in missions and milestones, we are learning to think in epochs. The next frontier will not belong to individual nations or even generations, but to the continuity of civilization itself. If our robotic emissaries are our first steps into the dark, then our eventual descendants, biological, artificial, or something in between, will be the next. The rise of advanced artificial intelligence and self-replicating technologies hints at a future where exploration might outlast humanity's physical form. Machines designed to learn, adapt, and repair themselves could travel where we cannot, carrying our knowledge, or perhaps our consciousness, into the galactic wilderness. The question, then, is not whether we can reach the stars, but what of us will go. Will it be humans, encased in hibernation vessels, dreaming their way through centuries? Or will it be data, our thoughts, memories, and stories, encoded in machines that evolve long after we are gone? Each possibility raises the same profound truth. The desire to cross the dark is not about escape. It is about continuity. To venture outward is to affirm that life, in whatever form, seeks to persist. And perhaps that persistence is the universe's own way of knowing itself. As we look forward, the great observatories, James Webb, Roman, extremely large telescope, Louvre, are already scanning the skies for exoplanets that might harbor life. Worlds with oceans, clouds, and even hints of biogenic gases have been detected hundreds of light-years away. Some are eerily familiar, blue, temperate, and sunlit. Others orbit red dwarfs, basking under skies of crimson. Each one whispers a possibility. We are no longer alone in our dreaming. The stars themselves have become destinations. And yet, as the data flows in, one truth becomes increasingly clear. To understand those distant worlds, we must first understand our own. The patterns of habitability, chemistry, and collapse that shape Earth are the same that govern every planet in the cosmos. The farther we travel, the more we realize how inseparable we are from the universe that birthed us. Our story, from the first spark of fire to the first signal from a probe beyond the sun, is part of a much older narrative, the universe learning to look back at itself. The Voyagers still drift in that darkness, their gold records waiting patiently for someone, or something, to find them. They may never be discovered, but perhaps that is not the point. Perhaps the message is meant not for others, but for us, a reminder that we were capable of curiosity, of courage, of wonder. To cross the dark is to accept our role as cosmic storytellers, the brief, bright flicker of awareness in an infinite night. And so we keep sending our voices outward, fragile, defiant, eternal, knowing that the silence may never answer, and loving the mystery all the same. Part 13, the long view. The farther we travel, the smaller we become, and the greater we seem. It is the paradox at the heart of exploration. Every step outward expands our knowledge and humbles our significance. From the first probe that crossed the moon's orbit to the Voyagers now gliding through interstellar space, humanity's reach has grown a millionfold. And yet, at every new horizon, the same truth returns. We are small, transient, and astonishingly fortunate to exist at all. The long view begins here in the acknowledgement of perspective. When Voyager 1 turned its camera back toward Earth in 1990 at Carl Sagan's request, it captured what may still be the most profound image ever taken. A faint blue, suspended in a shaft of sunlight. Every human who has ever lived existed on that pixel. Sagan's words still echo through generations. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. That pale blue dot became more than a photograph. It became a moral compass. Since that moment, every planetary mission, every camera that looks back toward home, has extended that perspective. Cassini saw Earth as a point of light through Saturn's rings. Mars Reconnaissance Orbiter photographed our planet as a gleaming crescent in the Martian sky. Even Bepi Colombo, bound for Mercury, glimpsed Earth during its slingshot maneuver, a glowing marble fading into distance. Each view reminds us that we are passengers on the same fragile sphere, clinging to warmth and air in a vast, indifferent dark. This awareness is not despair. It is clarity. For the first time in history, a species can see its entire home, understand its fragility, and consciously choose to protect it. That realization, born from the eyes of our machines, may be the greatest discovery of all. The long view is not about conquering space. It is about continuity, the understanding that exploration is a generational act, one that binds past, present, and future in a single thread of curiosity. The probes we launch today may not send their final signals for centuries. The data we collect now will guide civilizations that have yet to be imagined. In that sense, every mission is a message to the future. Perseverance's samples, sealed on the Martian surface, are letters to descendants who will one day return to retrieve them. Voyager's gold records are postcards to eternity. Even our telescopes, gazing at the birthplaces of stars, are teaching us not just where we came from, but what we may become. And the question that underlies it all remains unchanged. Why do we explore? Some say it is instinct, the evolutionary urge to push beyond boundaries. Others call it ambition, curiosity, or the hunger for survival. But perhaps, at its core, exploration is an act of reverence. To explore is to bear witness to existence, to look upon the cosmos and say, I see you, and I am part of you. This is the essence of the long view, to see humanity not as a fleeting species trapped on a small planet, but as one chapter in the universe's story of self-awareness. The discoveries of the past century, from Jupiter's storms to Titan's lakes to the potential oceans beneath Europa and Enceladus, have shown that the universe is not a lifeless void, but a canvas of possibilities. Even if we never find another civilization, the fact that we are capable of asking the question proves that the cosmos has, in at least one place, achieved consciousness. Every satellite, every rover, every probe is a continuation of that awakening. Our telescopes peer backward in time, to the first galaxies born after the Big Bang. Our landers dig into the soils of other worlds, searching for molecules that might have sparked life. Each discovery is a mirror held up to existence itself. Yet, perhaps the most profound insight of all is not about what lies beyond the stars, but what lies within. Exploration has revealed that survival, whether on Mars or Earth, depends not only on science and technology, but on empathy, restraint, and vision. To endure among the stars, humanity must learn to value not just discovery, but harmony. The long view demands patience. It demands humility. It demands that we see the cosmos not as a frontier to be conquered, but as a home to be understood. And it asks one final question, a question that every explorer, scientist, and dreamer must eventually face. What kind of ancestors do we wish to be? For when the ships of the future depart, when the descendants of Voyager and Juno and Perseverance leave the solar system behind, they will carry with them not only our science, but our legacy. They will carry our art, our music, our laughter, and our hope. And in that hope lies the best of what we are. Perhaps one day, far from now, in some other system orbiting some other sun, Another being will look up at their sky and wonder who else might be out there. Perhaps they will find one of our messengers, drifting silently through the dark, still playing a song, still bearing our message. We were here. We looked outward. We sought to understand. And even if no one ever hears us, the act itself, the act of seeking, will remain our greatest triumph. Because in the end, exploration is not about reaching the stars. It is about keeping the stars alive within us. Part 14, The Horizon of Forever. In every era, humanity has lived with horizons. First of land, then of sea, then of sky. Each one seemed final until we crossed it. Now, for the first time, we face a horizon without end. The boundary of the solar system is not a wall but an open door. Beyond it stretches an ocean so vast that even light itself takes millennia to cross. And yet, we gaze into that immensity with the same question that has guided us since the first spark of fire. What lies beyond? The universe answers in silence, but the silence is not empty. It is filled with the soft echoes of everything we have learned, the pulse of radio signals from our distant probes, the hum of stars vibrating in the dark, the faint memory of creation itself carried in cosmic background radiation. The more we listen, the more we realize that the universe is not separate from us. It is within us, as much as we are within it. Our story began on a small blue planet, orbiting an ordinary star on the edge of a spiral galaxy. From that fragile place, we built the tools to look outward. Stone turned to metal, metal turned to circuitry, circuitry turned to thought. We sent our voices into the void not to conquer it, but to join it. Each mission, Pioneer, Voyager, Cassini, Juno, Perseverance, has been a word in a cosmic sentence we are still learning to write. And now, as we stand at the threshold of interstellar space, the sentence continues, its meaning deepening with every discovery. We have seen storms that last for centuries, oceans beneath ice, and rivers of methane under alien skies. We have mapped the remnants of creation and found, in the chemistry of distant worlds, the same elements that form our blood and bones. We have begun to see the universe as a continuum, not of emptiness, but of potential. The horizon of forever is not a destination. It is a perspective. It is the understanding that the journey itself is the meaning. Somewhere, Voyager 1 drifts onward, its instruments slowly dimming as its power fades. One day, its voice will go silent. But silence does not mean death, it means continuation. The spacecraft will keep moving through the interstellar dark, long after the sun has cooled and Earth itself has changed beyond recognition. It will outlast cities, nations, and even the memory of its makers. And yet, on its golden record, it carries the laughter of a child, the song of whales, the heartbeat of a world that once looked up at the stars and wondered. That is the essence of the human story. We build small things that endure beyond our knowing. Perhaps, far in the future, another intelligence will find that record and decipher it. Perhaps they will learn that once, long ago, on a tiny world bathed in blue light, there lived a species that dreamed. Or perhaps no one will ever find it. Perhaps it will drift forever, a silent testament to curiosity itself. Either way, the message endures. We existed, and we reached for the infinite. Back on Earth, the place where all of this began. The stars still rise, the oceans still move, and the wind still carries the same molecules that once filled the lungs of our ancestors. Every grain of dust, every photon of light, every human breath is part of the same ancient rhythm that began when the universe was young. We are made of that rhythm. We are its memory and its witness. And so, the journey continues not because we must, but because we can. To look outward is to remain alive. To seek is to be human. Our probes will fade, our civilizations may change, but the impulse that sent them will not. It will echo in the generations to come, in the builders of starships, in the dreamers who watch the skies, in the children who will one day call another planet home. Each will carry within them the same spark that burned in the hearts of those who first looked up from the plains of Earth and asked, "What is out there?" And perhaps, one day, somewhere beneath a different sky, they will look back, not in longing but in gratitude. They will remember the small blue world that taught them to dream, the home that reached for the stars. When that moment comes, the circle will close. The universe, through us, will have seen itself, not as a collection of stars and planets, but as a living story, still being written. Because the horizon of forever is not a line we cross. It is the act of moving toward it, endlessly, courageously, joyfully. We will keep going. We will keep listening. We will keep wondering. And as long as we do, the universe will never be silent again. Part 15, Epilogue. The quiet between stars. There comes a moment, after every transmission fades, when the universe seems utterly still. No data streams, no signals, only the hum of space, a soundless whisper stretched across eternity. It is in that quiet that the meaning of it all begins to settle. For billions of years, the cosmos existed without an observer, without a voice to name its beauty. Then, somewhere on a small world of clouds and oceans, awareness bloomed. It built fire, language, and tools. It built dreams. And in time, those dreams became engines that rose through the air, pierced the sky, and carried that fragile awareness into the dark. Every probe, every telescope, every rover is an extension of that first gaze upward, the gaze that began with wonder and has never stopped. When Voyager sent back its final faint signal, humanity listened. When Cassini plunged into Saturn's clouds, humanity wept. And when Perseverance drilled its first Martian core, humanity hoped. We are a species of listeners. We listen to the stars, to the planets, to the echoes of our own creation. And in that listening, we hear ourselves. Perhaps that is why the silence beyond the solar system feels less like emptiness and more like potential. The pause between notes in a symphony too vast to comprehend. The universe is not mute. It is waiting. Waiting for the next question, the next attempt, the next messenger to carry the story forward. Because even when our machines fall silent, the story will not end. It will live in the data archived on Earth, in the photographs engraved on metal, in the starlight that reaches the eyes of those yet to be born. It will live in every act of curiosity, every experiment, every spark of imagination that refuses to be extinguished. In the centuries to come, when new explorers, human, robotic, or something beyond both, stand on alien shores and look back toward the sun, they will see what we once saw, a pale blue glow, faint and precious. They will know that their journey began there, on a world that dared to look up. And maybe, just maybe, they will whisper a greeting into the dark, the same way we once did, not to be heard, but simply to belong. The quiet between stars is not absence. It is breath, the universe inhaling, holding, and waiting for the next word.